Hi everyone, welcome back to Math 256. This is Scott. Let's get started. What we're going to talk about today is first off section 4.1, in which we will explore for the first time something that we'll be looking at quite extensively over the next few weeks, and that is first order systems. And by systems, we mean systems of differential equations. So here's the setup. So the setup is that we have x1 up through xn, so n variables, and they are all dependent on t. So these are all functions of t. And furthermore, we have a system of equations. X1 equals something. X1 prime equals something. X2 prime also equals something. On down the line until we get to xn prime, which also equals something. And the thing here in this column, so these only depend, these only involve the x1 prime up through, sorry, not x1 prime, they only involve the x1 through xn, no derivatives, and t, and these derivatives are all with respect to t. So these derivatives with respect to t. So these parts only involve the x's and a t, and then all these derivatives are with respect to t. So all derivatives are on the left, and it's all laid out like so. Alright, now the basic idea here is that we are going to learn various ways of analyzing these sorts of systems. So it'll be a goal of ours to put anything that is not of this form into this form through some trickery. So the idea here is that we will develop methods, and that will be both quantitative and qualitative, to explore and or solve this kind of system. So thus, one goal of ours will be to turn things that are not of this form into this form. Thus, we will want to be able to turn things of different forms into these first order systems. Alright. So now the first task that we're going to do is we're going to try to figure out how to turn higher order differential equations, single differential equations, into a first order system. So this is the first task. Task number 1. Turn higher order differential equations into first order systems. And this is going to be one of our primary tasks, and we'll explain why we would want to do this in a bit. But first, let's see just an example of the sort of thing we would want to turn into a system. So let's take, for example, x double prime minus x prime minus 6x is equal to e to the t. So this is a classic little example. It is one that we could easily do by the methods that we were just discussing in the previous chapter. We can find the complementary solution by looking at the characteristic polynomial. We can find a particular solution by using the method of undetermined coefficients. But let's now take on the task of turning this into a first order system. So the goal would be turn this into a first order system. And again, the reason for that we will develop as we learn more techniques. But for now, let's just consider what we're going to have to do here. So what we currently have is a second order single equation. So first off, let's just rewrite this in terms of its highest derivative. Rewrite with highest derivative isolated. So that would mean x double prime is equal to x prime plus 6x plus e to the t. Now, what we're going to do is we're going to declare a new variable to be the derivative of x. So then the idea here, so then let x1 just be the original x, and make new variables. Here we're only going to need one new variable out of the derivatives of the previously defined variables. So in particular, that means that x2 is going to be x1 prime, or in other words, just x prime. That means then, x double prime is going to be the same as just x2 prime. So then, the system of equations that we would get is actually now essentially sitting in front of us. So then, the system would look like this. Well, x1 prime, by definition, is just equal to x2. x2 prime is what the x double prime was. which is going to then be rewritten in terms of this x2 plus 6x1 plus e to the t. So this here represents, so this represents essentially the x double prime, this represents the x prime, this represents just the x. And now what we have is a first order system that involves nothing more than the first derivative of each of two variables instead of what previously was one single second order equation. And in general, it's going to go like this. And the highest, the order of the differential equation will then correspond with the number of variables in our new system. So note, the order of the original system, of the original equation will correspond to the number of variables in the system. Alright, let's try this again with something like this. So another example, let's take the equation x, the third derivative of x, so x triple prime, plus 3 x squared, not x squared, I mean x double prime, plus 2x prime minus 5x equals sine 2t. So what this means is we are going to want to first off rewrite this in terms of its highest derivative, so the third derivative of x is the same as negative 3x double prime minus 2x prime plus 5x minus sine 2t. Now the new variables that we're going to assign are going to be first x1, which will just be regular x, x2, which will be the first derivative of x1, which corresponds to the second derivative of just regular x, and we'll have x3, which will be the first derivative of x2, which in turn corresponds to the third derivative of the regular x. Now then, we just rewrite this as the system x1 prime equals x2. x2 oh, sorry. Stupid. Ignore what I just wrote. So this is just x prime. This is x double prime. And that would mean that x3 prime would be the same as x triple prime. Sorry about that. It's easy to lose track of which derivatives are which here. Okay, so then x2 prime is the same as x3. And then x3 prime, that is what represents the third derivative. And so it's going to be negative 3 x double prime. But x double prime is the same as just x3, and then minus 2x prime, which is just going to be minus 2x2 then, and then minus 5x, which is x1, and then, sorry, this is plus sine 2t. What a video. Alright, anyway, back to work. Plus sine 2t. Okay. All my negatives and, this is plus. Okay. For those of you following along, watch out. Typos galore. So this was plus. These should just be x prime and x double prime, plus and plus. Okay. Now, before we go any further on this, let's vaguely explain some of the rationale for why this is even a good idea. So the reason for doing this. So there are two main reasons. One is for the purposes of finding solutions analytically, and the other is for the purposes of finding a more qualitative, graphical, or numerical approach. So first off, one. So this is what we will be looking at coming up. This is the the analytical reason for doing this, and it is that we will be able to apply techniques from linear algebra to solve many categories of such systems. So that's one reason. We'll rewrite things in order to be able to apply linear algebra techniques to solve them. So obviously, some of the ones that we were looking at right now so far are things that have solutions that we can find by other means. But linear algebra is a useful subject that we will be able to apply for our own ends here in solving these systems. Remember, linear algebra is about systems of equations, and it can also be used for systems of differential equations. And then the second reason is that we can produce graphical representations or numerical approximations of first order systems more easily than higher order equations. But more on that more on that a little bit later, but for now, let's actually just say what these graphical representations vaguely look like, and then we'll take a crack at some more examples, and we'll look at what Bluffton has to show us. So direction fields. So this is what the system equivalent of a slope field is. So this is the two-dimensional system equivalent of a slope field. And what it does is it displays the relationship between two variables as an array of directed line segments. In other words, arrows. Then the solutions come in what are called trajectories. Solutions can be plotted as trajectories along the xy plane. So trajectories is what they're called. And what these look like is something like this. So we have y going this way, we have x going this way, and we have maybe an arrow, system of arrows going like so. And maybe one more row going like this. And then trajectories will be looking something like this, where it's just a pathway that is going through the plane in the direction indicated by the arrows. So it obeys the direction of the arrows, and then all of the points on this trajectory represent a pair of values x and y that would be associated in this particular solution. And then the trajectories are parameterized by the variable t that x and y both depend on. Then what you can also do is what's called a time plot. So we can represent x with respect to t or y with respect to t what that will look like is you'll have the x values just changing according to however the curve is parameterized. So then, for example, we'll have x with respect to t. So let's say it was this curve and it was going from down here up to here. So the x values are going down and apparently leveling off at an x value of 0. So maybe we have something like this. And conversely, again, if we take this case, we have y values that are starting off negative, growing, and becoming positive. So then maybe our y values are doing something like this. So our y values are maybe going like so. And then for the same t, the x-coordinate and y-coordinate would be given by the positions of these particular curves, and those would correspond to a point up here. However, one thing about these trajectories and these direction fields is that this only applies if the system is what is called autonomous. Note. We can only draw a direction field if the system is what is called autonomous, and this means the same thing, autonomous. System is autonomous, which means there is no occurrence of t on the right-hand side of these differential equations. So there is no t on the right-hand side. Otherwise, the direction field would be changing. Which could actually make sense in an animation, but it wouldn't make sense for a specific plot. So let's take an example. So as an example, let's take a modified version of the differential equation that we were talking about earlier. Namely, it would now have to be a homogeneous second order equation so that its system would be autonomous. So x double prime minus x prime minus 6x will now equal 0. Which then will give us the system x1 is going to be equal to just x, which means and x2 is going to be the derivative of x1, which is going to be the derivative of x, which means that if this is rewritten as x double prime equals x prime plus 6x, then that means that we're going to have a system, again by the same logic as before, that gives us x1 prime equals x2, and then x2 prime is equal to x prime, which is x2 plus 6x1. now we can plot the direction field and trajectories on the slope field generator from Bluffton. Now to see the video if you are just getting these notes from the PDF. The way you actually do this will be from the video, the YouTube video version of this lecture. So now let's have a look at that. Okay, so now we just go to the internet, you just look up slope field generator, just one of the first ones that comes up. You just you then just scroll down until you find the one from bluffton.edu. So that's the one that I prefer, and part of the reason why I like this one best is for this very feature. So you'll notice that we have been using one ordinary differential equation, but one of the options here is a system of differential equations. So now what we have is the opportunity to give dx dt and dy dt, and here we can use x will be x1 and y will be x2. So according to our previous system, we'll have dx dt equals just y. And then according to this one, we'll have dy dt equals y plus 6x. And that will give us our, so this is going to give us the direction field now. And let me change this to the Runge-Kutta method. That is what gives the best solution curves here. But then you just plop any point down and it will generate a trajectory. And you'll notice that these are all just going whichever direction they are going. And now, let me clear all these and we'll just focus on one specific one, 0, 1. How about that? Okay, so now if you scroll down a little bit, you actually get numerical solutions and also time plots. And in particular here, what we have is x and y each being plotted according to their position with respect to time. And notice that what they're making are and as far as this is concerned, all we're actually concerned about is the x. We can't help the fact that Bluffton is going to automatically show us both of them, but it turns out that in this particular case, we are actually not so interested, in fact, in the solution curve for the y, because y was a contrived variable that we invented in order to produce a system, but only the x is actually of interest to us. Now notice that it has the appearance of an exponential function, and that should make sense to us because if you remember the original system that this came from, it involved a second order with constant coefficients, and the basic form of those solutions is indeed an exponential function. Now notice over here there are different scales for the x and the y. The way Bluffton's system works is it automatically puts the x and the y together on the same diagram, but then it's got separated x and y scales color coded so that you can tell which one belongs to which. Now you can actually you can actually unlock the t equals 0 on the left and scroll backwards and get a little bit of the prehistory. Unfortunately, you are a little bit constrained in this, in that it doesn't actually let you go around changing the window of the x and y values in this particular feature, which is pretty annoying. But in fact, there are very few free software online applets that you can use that actually give you these time plots anyway. So all things considered, this one is what I think is the best because of this functionality that is not shared by as far as I can tell, really any of the other free online differential equation applets. You can get access to this kind of service if you use something fancier like a Maple or a Mathematica type system. But for the free ones, the ones that you want to just be able to access on the internet, it's hard to get a version that allows for the time plots. So anyway, that's how you can generate those. Alright, and now what we're going to do is we're going to go back to the analytic side of things, the business of actually turning things into and out of systems, and we're going to take a second order system and turn it into a bigger first order system. So that's another thing we can do. So note. We can convert higher order systems into first order systems and the way we would do that is by the same basic idea. Just going to take the different variables and their different derivatives, and that will serve as the place where we get our new variables. So as an example, let's take a second order system. X double prime is equal to 2x minus 3y, for example. Y double prime is equal to x plus y minus 20 sine t. So if we have a second order system like this, then we will just go through the business that we went through before, where x1 will just be regular x, x2 will be the derivative of x1, which is the same thing as just the derivative of x. And then what that means is x2 prime is actually going to be the same thing as just x double prime. So that puts that first equation there all into first derivatives of variables x1 and x2. As for y, we'll go through the same business. y1 will be just the original y. y2 will be the derivative of y1, which is the same as just the derivative of the original y. And then we can say that y2 prime is the same as actually just the second derivative of y. Which then means that if we take our original system, we can expand that out into a bigger system by changing the x prime and x double prime into x1 and x2 and x2 prime. So what we have here is that x1 prime equals just x2, x2 prime equals 2x1 minus 3y1. We've got y1 prime equals y2, and y2 prime is equal to x plus y, which is x1 plus y1 minus 20 sine t. Alright, so that is how we would convert a system of higher than order 1 into a bigger system of that lower order. Basically, whatever the order of the equations was, that's how many new variables we're going to have to, that's how much we're going to have to do to add the new things. So the order 2 means we're going to have 2 variables for x, order 2 here means we're going to have 2 variables for y. Now, one last task here is that we can actually, if we want, convert backwards. We can convert from a system into a higher order differential equation if we wish. So note, we can go the other direction and turn a system into a higher order equation. For example, let's say that I had something like this. x1 prime, actually I'll just make it in terms of x's and y's. It's a little bit easier when you only have 2 variables to just make them x's and y's instead of x1 and x2. So let's go x prime equals x minus y, and y prime is equal to, let's just say, x plus y. Now, the way this is going to work is that we essentially are going to go through a very similar process to what we did before, where we're just going to now take it in reverse, and we're going to say that x equals x, and we're going to say that y is equal to x prime. So then what that means is that y prime is going to equal x double prime. And now what we can do is we can take the original system of equations in 2 variables and make them a combination of x primes and double primes, and we can hopefully try to figure out a way to put them all together into just one equation. So x prime here is the same as just a y, or vice versa. X prime equals x minus y, which is x prime. And then what that means is, if I add that to both sides, that means x equals 2 x prime. And then that I can in turn put into here. So that's all that from that. Over here, I can rewrite this as x double prime equals x plus x prime. And now I can just take this and put that in for just the x here. And I would get x double prime is equal to 2x prime plus x prime. So in other words, x double prime is equal to 3x prime. So we now have a single second order equation in place of our previous system of 2 first order equations. And sometimes the techniques you would have to use here would involve maybe a little bit more little bit more sophisticated linear algebra. But this is not a direction we're going to go very often. In the next section, we're going to learn more explicitly how to actually solve the systems themselves in many circumstances, and so it'll usually be more convenient for us to turn things into the systems rather than turning them back out. But it's just an interesting side note that we can, in fact, go the other direction should we desire. Alright, well that'll do it for now, and I'll see you in the next episode of Math 256. Till then, bye!